So this kind of just summarizes a lot of the things we've been talking about with respect to wellbore stability. And here the question is essentially, should we case or not case the well? And they took this sort of comprehensive approach to build up this plot, which includes many aspects of wellbore stability. So before we had like required CO or breakout widths or whatever, and in this plot they sort of are plotting some weighted measure of stability that incorporates a lot of those things. And unlike before, where we always, or the plots that we looked at before, were always symmetric, right? You could look at any one quarter of it and reproduce the whole plot, right? But that's not the case here, because in this case they actually had they had some information about the heterogeneity of the reservoir, right? As you go around. So remember, in the lower hemisphere projection plot, each of those places, each of those points represents some angle of deviation and some azimuth that the well was drilled. Well, of course, you're not going to have the same strength material everywhere, right, in the earth. And so in this case, they actually had some model for the variation in strength of the rock, and then that's why in this case you get this sort of unsymmetry there. And so the idea, is that the cool colors are more stable regions, and the warm colors are less stable regions, which the less stable regions would require additional mud weight while drilling, would produce larger breakout widths and would require larger rock strengths for stability, right? So they did this, what they call a comprehensive geomechanical study. And by the way, it's covered in the book. I've got the reference for the figure here in chapter 10, but there's also a more detailed information in this paper. So SP 52-186. This was in the Cook Inlet, Alaska. So if you want more information, I would recommend reading the paper, because it's more details than in the book. But nevertheless, anyway, they did this comprehensive geomechanical study and came up with this plot, and then they claimed that after the fact, after they did it, they realized that there were a couple of horizontal wells already drilled in the area. You can't see one sort of drilled here to the northwest, and one drilled here kind of to the northeast. And if you see where they lie on the plot, right, the one to the northwest ends up right in this sort of, they were both horizontal wells. So the one to the northwest ends up right in this cool area, and the one to the northeast ends up right in this kind of hot area over here. And they claim that that the evidence from drilling those wells corresponded with what they, comprehensive geomechanical model said, in the sense that the one drilled to the west, they had no problems with stability. However, the one drilled to the northeast, they did, and they had to make several corrections along the way. So I think what they were looking for here was they were going to drill multiple laterals from single vertical wells, and so they were interested in the rock strength variations at different depths, because whenever you kick off from a vertical well, you want to do it in an area that has high strength, right? So for stability reasons. So they were able to develop some type of this should be MPA, some type of empirical model for the rock strength. So this came from cores. So they had some core samples. they were able to develop this empirical model so that when they were doing logging-wide drilling, and just using the sonic measurements for the compressive sound speed, their VP, then they could estimate what the unconfined compressor strength was. And again, this was to determine where the highest strength areas were for the horizontal kickoffs. And they also use this information to do some additional studies on the effect of breakouts from sand production. So far we've only talked about breakouts in terms of drilling, right? But sometimes the restrictions on breakouts and wellbore stability can actually be more restrictive during production. So what happens during production is, you know, you're actually bringing reservoir fluids to the wellbore region, which changes the effective stress and could cause breakouts associated with that. So when you're trying to make a decision on whether you want to case a well or not, you also have to take into consider the effects of production, not just drilling. Right? So a well that was stable during drilling might turn unstable during production, and that would be very bad. So in this case, they looked at two different drawdown scenarios. One was a 500 psi slow drawdown. So I think what they, if I recall, what they meant by slow was, I think the difference was like 10 minutes and 1,000 minutes or something like that. So they investigated a 500 psi. They were different by an order of magnitude. I don't remember exact. A couple of orders of magnitude. I don't remember the exact numbers, but the idea here was that if you look at 500 psi drawdown over a long period of time versus a 1,000 psi drawdown over a short period of time, how that affects the breakouts. And the reason that the rate matters, of course, is because you're talking about how fluids diffuse, right? And diffusion is a very slow process, and so you can have rapid changes in the effective stress if you draw it down too fast. And then it doesn't allow the sort of the fluid to come into the wellbore and be produced. So here what you're looking at are much higher fidelity models, and that's part of the reason. I mean, really, this is the only reason I wanted to show you this stuff. This is a far more high fidelity model than anything we've talked about. So these are full finite element simulations. Right? So does anybody know what? I know I've probably said it in the class several times, but does anybody know what finite elements are? Like finite element simulation? So we know, like, for example, the Kirsch equations. They're the solutions to an elasticity problem for a, the actual conditions for that problem are an infinite medium, right, which is actually well approximated in the Earth. It's more or less infinite, right? But an infinite medium with a hole in it, right? Well, if you go to the laboratory, you can't reproduce this, right? I mean, you have fixed size samples, and so even in the laboratory, the Kirsch equations aren't truly valid. If your hole is small relative to your sample size, then it can be well approximated by that, right? But there's certain assumptions, but the kind of most glaring assumption is that there is a circular hole, right? So as soon as you don't have a circular hole, Kirsch equations are no longer valid. Right? That's the only thing we used in this class, right? Because it's sort of what we can solve by hand. Right? But in real life, if you have a hole that's, well, first of all, possibly not circular, maybe just due to key seeding or something, right, during the drilling process, that then experiences some additional breakouts as well, right? So you have a hole like this. Well, how do you really know the stress state around it? And one way to do it is something called finite element modeling, right? So in a finite element model, we would take the exact geometry in some representation, and we discretize the domain, right? So we would essentially, because we don't know the solution of the elasticity equations exactly when you have some arbitrary geometry, what we do is we discretize the domain. That is, we break it up into little pieces. We call the little pieces finite elements, right? Something like this, right? Of course, in real life, you would want to have a really you don't want to have a conforming mesh. This is called the mesh. You'd want to have a conforming mesh to the hole, so you would use much smaller elements around the hole, and you'd grade them. They'd get larger as you went away from the hole. But nevertheless, you take your real geometry, your real domain, and you break it up into these little pieces called finite elements. And we can solve the elasticity equations on these finite elements. Okay. If you take reservoirs, is anybody going to take a reservoir simulation from me in the fall? Yeah. Everyone? Several people? You can just leave your pens at home for that class, because that's going to be all coding. Anyway, so in that class we use something called finite differences, which can be shown to be a special case of finite elements, in fact. So in a finite element, what we do is over every little element we interpolate a field. Right? So we use like a linear interpolation to interpolate a field. In the case of like this problem, would be the field would contain displacements and pore pressure. Right? And so if we want to know the displacement or pore pressure at any place in the domain, then we can use a linear combination of our interpolating functions and unknowns that we solve for at the corners of the elements. Okay. So usually in finite elements we use piecewise linears, right? So if I want to know the pressure there, it would be a linear combination of 4 basis functions and the unknowns at the nodes, and that's what we actually solve for. Okay. So finite differences, you can derive them different ways, but in a finite difference approximation, what we assume is that the entire cell just has one value, right? So like in reservoir simulation, at least initially, we're just going to solve for like single-phase pressure diffusivity equation. So we would assume that the entire cell or element would just have one pressure. Right? So and in reservoir simulation, you'll actually see how I derived the equations from what essentially, I don't think I really introduced it this way, but essentially it's a finite element sort of way of deriving it. It makes it easy to go later from finite differences to finite elements, which finite elements are a higher level of approximation. Yeah.
So in this application of finite elements, do you use different elastic equations, or are you using the smaller curvature?
No. So yeah. So that's the difference. Is in this element has no knowledge of the fact that there's a hole right there, right? The Kirsch equations are a full field solution. It's a solution for the stresses everywhere, right? What we do in a finite element simulation is we actually solve conservation of momentum on every one of these cells, right? And while this cell doesn't know that there's a hole there, there's a cell right there that is touching that hole, and then on the edge that it's touching it, there's some type of boundary condition being applied, right? Like, it depends on if you're talking about drilling or production, right? But if it's a production, you could say set bottom hole pressure along this surface to some value, right? That'd be what you'd produce at. Well, then they're all interconnected. So what eventually would happen, we're going to solve conservation momentum there, but it's tied to that guy and that guy and that guy, and that guy is tied to these guys. And eventually, since they're all, you actually solve for everything simultaneously, all of the unknowns, then ultimately the displacements here are affected by the presence of the hole and the pressure boundary condition at the hole. So you actually solve for all of these unknowns at the same time. Right? And when you obviously you do this in a computer because this thing could be millions of unknowns. Right? So anyway, yeah. So these are, what you're looking at here are finite element simulations, right? So you're not seeing the mesh there, but it's there. And around the hole, what you see is something, these are contours, if you can read that, it's called equivalent plastic strain, right? And so if we go back to our kind of stress strain curve, right? We know that unconfined rocks sort of have a stress strain curve that looks like that, right? It's linear elastic, and then it fails, and it breaks. But if you have sufficient confinement on rocks, then we'll have some inelastic region, right? So if you confine it like a little bit, then you might have something like that. If you confine it a little bit more, it might have something like that. If you confine it a little bit more, you might have something that looks like this. And this, if you were to sort of run it through this stress strain cycle and then unload the rock, it was going to unload elastically. And this distance right here is going to be what we call the equivalent plastic strain. Okay? So sort of what you're plotting here in those color contours looks like, you know, it's this equivalent plastic strain. And so if you have a sophisticated enough failure model, it can model all this sort of complex post-elastic behavior, okay? So in what we did so far in the class was we just looked at Moore-Coulomb. And what Moore-Coulomb says is that, you know, if the stress is above that line, then the material's just failed. Right? But again, a rock with sufficient confining pressure doesn't just fail in the sense that it loses all its strength. I mean, you guys have seen this in your labs probably, right? You can continue to strain that rock. And what it does is it just, if you continue to strain it along a loading path that is sufficient, has enough shear stress, then it's just going to continue to slip or slide without additional force, right, up that line. And so what these curves represent are actually more complex behavior in that this guy is actually strengthening as it's sliding. So it does require more force than it did, you know. So, and eventually, when you get to something that maybe looks like this, where it actually softens, this would be due to pore collapse. Right? So the material, you're continuing to load it, and then eventually you'd collapse pores, and then it would weaken and soften a little bit. So the more sophisticated material model than what we looked at some of them, right? But we didn't really solve problems with it, okay? A more sophisticated material model that had this type of complexity could be used in a finite element simulation to compute these contours of equivalent plastic strain, and it's this equivalent plastic strain then that is tied to the wellbore breakout width. So there's some criterion that says, you know, once the rock has gotten to like 4% equivalent plastic strain or something, then that's where you'd expect to have a breakout. Right? And if you go to even more complexity than this, you can actually model the material separation. So the type of modeling that I do in my research with my graduate students is we actually model material failure. So if I were to simulate this with our tools, you would actually see the material flaking away as it was breaking apart, and you would see the actual contour of the breakout. Yeah.
Just curious. So I'm assuming that the finer your first blocks are, the more computing power you need.
Yeah.
Is there a way to like predict how long it'll take to run the simulation without actually running it? Just like you can determine the
That's a hard. In a time-dependent problem, it can be difficult. If it's a steady state problem, then you have a simple matrix inversion, and you could probably sort of determine the number of sort of flops needed, right? Floating point operations needed to solve it. You could come up with an enclosed form that would be a function of the element size and other things. If it's a time-dependent problem, that adds another bit of complexity, and it can be very difficult to estimate ahead of time. But what doesn't really matter? I mean, who cares how fast or how long you can solve the problem if you don't know it's correct, right? What's more important is, with respect to the grid block size or the finite element size, is to have a converged answer. So we have mathematical theories that tell us that in the limit, as these little finite elements get littler, get small, in the limit as they reduce, they will recover the exact analytic solution, right? We have a theory that'll tell us that, okay? But in practice, you can never actually run these to infinitely small, right? So you have to have some acceptable, good solution. And so then we use rules of thumb for that. And so typically what you would be asked to do is you would run several simulations of the same problem, the same boundary value problem, with successively finer meshes. So you'd say one like this, and then you can imagine if you just cut all of those in half, right? Then you did it again, and then you did it again. And what you would look for is the solution to the amount the solution changes to be very small. Like, from one successive refinement to the next should be like less than 10% change in the answer. Right? So that's what you would look for. That's called a convergence study. Yeah. And then, of course, in the really advanced sort of mathematical theories of finite elements and other things, we can actually develop error estimators. So we can come up with a priori estimations of where we'd have the largest errors, and then we can use that to refine only in those regions. So in this problem, you really wouldn't create a mesh like I have it drawn. Your mesh would be very fine near the hole, because that's where your highest stress concentrations are going to be, right? Out here, it's not going to be a lot of stress. It's not, there's not a lot of gradient in stress. And it's the gradient that matters, right? Because again, we would start off with something like a piecewise linear interpolation, right? Well, if you have a very high gradient in stress, you need a lot of elements for a piecewise linear to match that function. You understand? Right.
Which finite element software was used in this case?
I don't know. Maybe they mentioned it in the paper. I'm not sure. Yeah. If you're interested in commercial finite element software, there's, kind of the bigger ones are Abacus, ANSYS. I think both of those can do poroelasticity, which you need to solve this problem. There's a newer one called COMSOL, which sort of gives you all the element technology and solvers, but allows you to put in the physics. And so that one you could essentially code up your own, not code up. I shouldn't say code up, because I don't want it to sound intimidating. But let's say input. You can input the PDEs, and then it gives you all the element technology and solvers and everything. So anyway, just to sort of wrap this up, then the point is that they use a much more sophisticated method here to develop, what the breakout widths would be, that include a more complex constitutive model and an actual finite element simulation of the results for the different